Okay, so after talking about and introducing operational amplifiers, we talked about 4 op-amp circuits. Non-inverting amplifier, inverting amplifier, adders, and differencing amplifiers. Now we're going to change the circuit a little bit and place a capacitor in the circuit and talk about differentiating amplifier. Let's see what happens in this circuit. I'm going to do the same thing. I'm going to apply my op-amp rules, which is I positive is equal to 0, I negative is equal to 0. Then I have V positive is connected to 0. Based on that, we can say that V negative should also be 0. Okay? Now, let's write a KCL at V negative. What should I write? KCL at V negative. Look to the left, okay, from the negative terminal, negative input terminal, or the inverting terminal. Look to the left. What's the current leaving that node? Negative C dV in, or let me actually write it like that. It's better to write it like that. C d over dt 0 minus V in. If you remember that for a capacitor, we had this formula. So I applied that here. What is the current going to the right from that node? 0 minus V out T over R is equal to 0. Do you agree with the KCL? Okay. Now, I'm going to keep V out, or I'm going to take V out to the other side so it becomes positive. So V out over R is equal to negative C dV in T over dt. And based on that, I can write V out is equal to negative, oh, I'm using RF, sorry, I should write RF. Negative RF C dV in over dt. Okay, question. What is this circuit doing? If you look at the red box. First, let me explain what do I mean by this question. Whenever I ask you, what is this circuit doing, it means that what happens to the input on its way to the output? So what happens to the input of this circuit on its way to the output? It gets differentiated. Do you see that? The output is equal to some coefficient, RFC, which is just a scaling, and a negative sign, which you know the only meaning that it carries is flipping the signal around the horizontal axis, or changing the phase. But the important part is that it takes the it takes the derivative of the input and gives it to the output. So that's why we call this circuit differentiating amplifier. For example, if you look at the input, a triangular wave, let's just let's use T1, T2, T3, and T4. Let's see what the output looks like. Okay, what is the derivative between 0 and T1? It's a positive number, right? And constant. Do you agree that it is constant? Because it's the line, it's a line. So it's a constant positive number. Then it will be multiplied by a negative number, so it will be a negative constant number, right? So how about between T1 and T2? The slope is negative, negative constant, multiplied by a negative number, it will be a positive constant. Again, okay, that's a differentiator circuit. It's a rather useful circuit in electrical engineering. Any problem in understanding what happens in this figure and what happens to the math? Okay. Let's swap places for resistor and capacitor and see what happens now. Okay. I'm going to call the voltage across the capacitor VC here in this circuit. Of course, because everything is a function of time, I'm writing it as Vc of t. And also I'm calling this current I. So, or IC, let's call it IC of t. Just to can someone give me a relationship between VC and IC? In fact, can someone give me VCT in terms of ICT? What should I write? Tell me. 1 over C, CF actually, the integral from T naught to T. What should be inside the integral? IC T prime dt prime, and then plus VC T0, right? That's the equation. Okay, now, when analyzing this circuit or any circuit, we want to answer one very important question. What is the circuit doing? So in order to understand that, do you think this equation is a useful one? Is a useful equation to tell me what the circuit is doing? Or no? For example, let's look at the previous equation, previous circuit. When I looked at the final equation, it's clearly stating that the output is proportional to the derivative of the input. That's exactly what I'm interested in knowing for the circuit. Output matters in terms of input. Now for this circuit, is the equation that I've written useful enough to tell me what the circuit is doing? I would say no. Why? Do you see the output in that equation? Do you see the input in that equation? What variables are involved in that equation? Two variables that you created yourself. Okay? So there's no trace of V out and V in. So all you're saying is that a capacitor equation, what is this? It's just a capacitor equation. It's saying nothing about the circuit, right? So let's change that. Let's get rid of VCT and ICT and replace it with more appropriate variables. For example, let's apply the op-amp rules. So this is I positive, 0. This is I negative, 0. V positive is, I'm using green. So this is V positive, which is 0. So is V negative, right? Now, can you replace VCT by a better expression of variables? VCT is equal to 0 minus V out. How about ICT? Do you agree that this current here is also ICT? Because it doesn't have anywhere else to go? Do you agree with that? ICT goes up. So can you give me a better expression of ICT that is useful for my understanding of the circuit? V in of t minus 0 over R. Now let's substitute these two into the equation. Instead of VCT, I will write negative V out t equal to 1 over CF integral from T naught to T. Instead of IC T prime, I will write V in T prime over R dt prime plus VC T naught. Okay? Now look at this equation. It's much better, right? Because it involves V in and V out for you, which means it's giving you an input-output characteristic of the circuit. So let's multiply both sides by a negative sign so we can single out V out. And I'm going to take R out of the integral and put it at the denominator here. Remember, I multiplied both sides by a negative sign. Now, look at this equation. Is there anything bothering us, any unwanted variables? You might point to VC of T naught, but remember, that's the initial voltage stored in the capacitor that usually you have access to, okay? So it's not a problem. It's not a variable. It's just some value, some constant. So what is this circuit doing? The important question. What happens to the input on its way to the output? It gets integrated. See? Again, this is actually much more important than the previous circuit. Very important circuit, integrator in electrical engineering. Okay? Any question? No? Yeah.
Would the bounds of the integral be flipped since you multiply by -1, or is there a reason why it stays the same?
If you want the bounds of the integral to change, then you shouldn't write that negative sign behind it. You can either put the negative sign to, see, let me write it like that. So you have this one. If you multiply it by a negative sign, what can you write? You can either write negative a, b, c, or you can write it as a, negative b, c, right? Now, look at that. When you are multiplied by a negative sign, either give the negative sign to this guy or to the integral. If you give it to the integral, the bounds are flipped, but I gave it to the coefficient. Did that make sense? See, they are multiplied, so only one of them gets the negative sign. Any problem? Question? No? Okay. Please start your mini lab. Just a couple of notes.